symposium. 4 talks, and then lunch will be at about 1 o'clock in the faculty club. Graduate students can eat for free, but you must register for the symposium if you want to get your free lunch. So register in the business office. Let's see, I guess that's about it. So, Bert?
Well, it's a pleasure to introduce today's speaker. I have admired him for some time by reputation, and now to be able to have him here. He was written up in CNE News last year for the 50th anniversary of the kinetic isotope effect, which he developed the theory for with one who won the Nobel Prize for the nuclear model, Maria Geppert-Mayer, and has established an area of research developing the theory and going on and developing more theory, and then the experiments which prove the theory, which is frequently done the other way, the theory after the experiment, but in this case before. So it's a pleasure to introduce Professor Jacob Bigeleisen, who will give us reminiscence of isotopes then and now.
Well, thank you, Dr. Davis. I'm indebted to you and the people at the University of Kentucky for inviting me here today. And it'll be a pleasure to tell a little bit about how things were in the whole field of isotope chemistry when I got into it, and some of the exciting things going on now. But let me start off with a little historical background. All of you know that isotopes were discovered in 1913 by Frederick Soddy, working with the natural radioactivity of heavy elements. Before Soddy's work, Madame Curie had isolated radium, a product in the decay chain of U-238 with a half-life of 1,590 years. And what Soddy found was a product in the thorium chain, which had the same chemistry as Madame Curie's radium, which in Soddy's radium had a half-life of 3.6 days, and so he called these isotopes substances that have the same place in the periodic table. Isotopes stand in the same place and have the same chemistry. Well, back in 1918, Aston, who did a lot of work on discovery of isotopes with the mass spectrometer, raised the question, could isotopes have different chemical or physical properties? So he posed this question to F.A. Lindemann, who incidentally was an Englishman, even though he has a German name, who was a student of Nernst, and Lindemann made a calculation of the possible differences in vapor pressures of lead isotopes. So could we have the first slide? Oh, no, I'm supposed to show transparency, so.
It's on the top.
Okay. From the Nernst theory of the heat capacity of a crystalline solid, you integrate it, you get the entropy, and you integrate that, you get the free energy. You derive this equation for the logarithm of the vapor pressure of a light to heavy isotope is equal to this number times theta, which is the high temperature of the crystal, and delta is the mass ratio of the heavy light isotope -1. And he calculated that at the melting point of lead, theta over T16. At that time, people didn't know whether vibrational energy had 0-point energy. And he said there would be a vapor pressure ratio of 1/50%. No 0-point energy, 5% in the opposite direction. 30 years ago, I gave a lecture on the vapor pressure problem, and I put these numbers into the Lindemann equation, and I found out this is really 1/500%, and this is -1/10%. Well, Lindemann didn't stay in science too long. He became a science advisor to Churchill. He became Lord Charwell and Baron Charwell, and he was in charge of the British military strategy in World War II. All right. So now, in any case, you see Lindemann's paper was published on the 1st of May in 1919. So isotope chemistry is a rather young subject, one day older than I am. Now, since Lindemann's day, lots has happened in this field. So you have equilibrium isotope effects and kinetic isotope effects. And from that, you can do engineering and you can separate isotopes. You can elucidate naturally occurring processes in geoscience, atmospheric science, marine science, and so forth. You can elucidate molecular structure, molecular forces, which application in inorganic physical chemistry, solid state physics, material science, polymer science, statistical mechanics. You can elucidate reaction mechanism, organic, mechanical, biochemistry, biophysics, ecology, medical science. And I understand I'm supposed to lecture on each one of these topics today. Maybe be a little too long, I think. We're supposed to get out of here by midnight. All right. Now, let me orient you about how big these differences in chemical properties are. Just for example, let's consider differences between protium and deuterium. The vapor pressure ratio of hydrogen, dihydrogen, HD is 1.7 at 20 degrees Kelvin. The vapor pressure ratio of protium water to deuterated water, 107. In a chemical reaction at room temperature, deuterium favors water over dihydrogen by a factor of 3.5. And in the electrolysis of water, light water is electrolyzed between 3 and 7 times as fast as heavy water, and that's a kinetic isotope effect. Now, what are these isotopic differences due to? Let's just consider a simple chemical reaction when I spoke to previously. Reaction of dihydrogen with water in which you exchange the deuterium for a protium atom. Well, we know as a result of quantum mechanics that if you have a potential surface, a light isotope has a larger 0-point energy of a heavy isotope, and this difference depends on shape of the potential, and a weak potential has a smaller difference than a steep potential, and in the approximation that all molecules are in state and that there's no entropy effect, then the equilibrium constant just depends on 0-point energy differences. And you can see this difference is larger than this, so the deuterium concentrates in the water. Now, in real life, all the molecules are not in the ground state, and there's this entropy problem to be taken care of. So the first attempt to do this was by Urey and his collaborators in the early 30s. After Harold Urey discovered deuterium, he applied the straightforward methods of statistical mechanics to calculate the equilibrium constant in a chemical exchange reaction. And for the hypothetical reaction between a light and a heavy isotope, here's a conventional equilibrium constant. And according to statistical mechanics, you can write that as a ratio of partition functions. And I'll tell you what that is right away. And then for the separation factor, which is the ratio, isotope ratio in one chemical species to that in the other, that's alpha. There's a mass factor, moment of inertia, 0-point energy, and an excitation factor, and I'll give you one of those. The mass factor is simply ratio of molecular weights. The moment of inertia factor is ratio of moments of inertia. The 0-point energy factor is the difference in 0-point energy, and the excitation factor is the ratio of Boltzmann excitation terms. So that's what people did in the 30s, and if we can have the first slide. This is a calculation by George Murphy, who was one of the co-discoverers of deuterium with Harold Urey, and the other one was Ferdinand Brickway. And he calculated the equilibrium between dihydrogen and HI as a function of temperature. He published this result, and there were experiments in the low temperature region of Urey and Rittenberg and Christ and other people, and they confirmed this. And actually, my recollection of this curve was when I was a graduate student in Berkeley and before the war. And in those days, they didn't teach quantum chemistry, even in graduate school in Berkeley. And Kenneth Pitzer had a seminar in quantum chemistry. And he used this as an example to show what one could do by quantum and statistical mechanics. And he pointed out very interesting kind of things that you find here. This equilibrium constant is a maximum, and then it goes through the minimum, and what happens afterwards, we'll find out in a little bit. Okay. Now, if we can have the next slide. In 1943, Willard Libby made calculations for the Exotopes exchange of protium, deuterium, and tritium between pure waters and mixed water. And I have his results. Let's just consider H2O and D2O. The underlying ones in 1943, 4.1, 4.17, 4.18. That'll be all for this slide at present. Can we turn that off for a minute? Well, in 1943, I worked on the Manhattan Project, and I was a spectroscopist in those days, and I was doing experiments measuring spectra of uranium compounds to see whether it would be feasible to separate uranium isotopes by some photo process. We did a lot of interesting spectroscopy, but by the summer of 1943, Maria Mayer and I were working on this, came to the conclusion that, while this was a lot of interesting science, this was not going to lead any place useful during World War II. And we were affirmed in this conclusion by a committee of Richard Tolman and James B. Cohen and E.B. Wilson Jr. So they recommend that we stop this project and people like me work on other things. So I was then assigned to prepare a summary of that project when I got a visit from a former student of Yuri's, who I was an assistant of his, and he came to see me and he said, well, you know all about the spectra and structure of uranium compounds. And I said, well, I don't know all about it, but what does ours know? Which isn't very much. I know that. He said, well, now here's this equation of Uri and Greif. You just put all your numbers in there and you calculate whether it's possible to separate uranium isotopes by chemistry. He said, well, I'll try and do it, but I don't know anything about this field, and I'll have to look into this Uri-Greif equation and so on. And he was rather annoyed with me, and he went down and saw Harold Urey, and he said, this man Bigeleisen is very cooperative. He doesn't realize there's a war on, and we've got to get on with this job. So I looked at that Uri-Greif equation. And I saw that there were ratios here for each species, and then you had to divide one by the other, and eventually you ended up with numbers, some of which were larger than one, some of them smaller than one, and eventually for your uranium compounds, you might end up with a number which is of the order of 0.1%, and was it larger than one, smaller than one, the final answer? Some of these factors larger than one, some smaller than one. I said, well, in chemistry, you measure differences. If you measure an equilibrium, you measure free energy differences. And the only thing you do in equilibrium chemistry on an absolute basis is you measure heat capacity relative to absolute zero. You assume that it's zero there. And from that you calculate the entropy, assuming the entropy at absolute zero, but everything else, enthalpy difference, free energy difference, even in physics, all energies are energy difference. Gravitational field, electrical field, magnetic field, you always measure difference. So I said, well, why don't I try and see whether I can calculate this fractionation factor directly as differences. Well, so I started to work on that. And I made quite a bit of progress. And after about 5 days, Maria came to see me, and she said to me, Jake, how are you doing with that summary report? I said, well, Maria, you know, I'm not working on this now. She said, why not? I said, well, I've been given this problem by Professor Yuri. She said, what is this problem? I explained it to her. And she said, well, what are you doing about it? And I told her what my approach was. Now, she was an expert in this field. She had already published work in this field with the Uri-Greif equation. And earlier, Dr. Davis reminded me about her work on statistical mechanics with Mayer, Brunauer, and Mayer. One Mayer was her husband, Joseph E. Mayer, and the one was Maria Mayer. And Brunauer was a great catalytic chemist, so on. So she said to me, you know, Jake, this is very interesting. Do you mind if I join you in this? I said, well, that's great, you know. I'm just a newcomer, and you're an old expert in this field. And so I could learn a lot. And she was a person with a very fast mind. She said, well, you just add one more term to what you've done, and that solves the problem. You're all done. So, what did we do? Can we have the next slide? Whatever it is. All right. She didn't write all this thing down at present. Eventually, I figured this all out after that meeting. In classical mechanics, partition function ratio is only a symmetry factor, which doesn't lead to any isotope, times the ratio of atomic masses, because we have atoms. Now, in a chemical reaction, not in a nuclear reaction, in a chemical reaction, no atoms are destroyed. Whatever atoms go in on one side come out on the other in different chemical species. But the atoms are the same, and their masses are the same. So in a chemical reaction, this product appears in the reactants, appears in the product. When you take the ratio, that goes away. This gives nothing. So in classical mechanics, you cannot separate isotopes. That's the first thing. So the logical thing is to see how the real world, quantum mechanics, differs from classical mechanics. So we define a free energy function, which is simply this ratio. And that's very easy to write down. This is equal to a product of the following. Here's the zero point energy. Here's this Boltzmann factor. I had already done this. And you may have said, you just add this back. That takes care of this, and you're all done. Okay? So that's all done. And now, let's see what happens. Can I have the next slide? So here's this reaction that I showed you, H2 plus Di, and this goes from low temperature to high temperature. And you see there is, in fact, a maximum, but there's no minimum, and at infinite temperature, the equilibrium constant goes to 1, like the classical thing, and there's no isotope chemistry. And that is it. And the problem which you encounter is that in the Bragg and Murphy case, you see they had all these small differences, get small at high temperature, and with the kind of calculations you could do then, you couldn't do it practically to get the right answer. Now, how well can we do on an absolute basis comparing theory and experiment? The next slide. This is this reaction I spoke about earlier between water and dihydrogen gas. And this has been studied ad nauseum by different people. And these are always circles of experimental points over a large temperature range. You can see this is about 600 K, and this is 300 K. And this solid line is not a least square line. This is a line calculated by my colleague Max Wolfsberg from first principles using the Bigeleisen layer equation from the known properties of the water molecule, the dihydrogen molecule. There are no adjustable constants, and you can't ask for anything better. That's it. Now, you might say, well, how does this do with heavier isotopes? Let's look at the next slide. And this is the exchange of oxygen 18 between carbon dioxide and water, and this has been studied over a large temperature. And the interesting thing you see here now is the previous slide I showed you was a plot against 1 over T, is a plot against 1 over T squared. And you see that over most of the temperature range, this follows the 1 over T squared law. So what is going on here? Why do you have 1 over T laws and 1 over T squared laws? So I'll explain that to you now. That'll be all for the slide. The first thing I had done with Maria was to expand this equation in powers of the 0-point energy difference. And the first term you get, we call the free energy function. That's m equal to this thing. And this g of u function has the following properties. It's always positive, and it has a value going from 0 to a half, 1/2 at low temperature, 0 at high temperature. So this tells you right away at a high temperature, isotope chemistry vanishes. You go to the classical limit, and at low temperature, you go to the 0-point energy limit. Tells you that right away. This function u is simply h over kT times the vibration frequency. Now, we also made another expansion, and we expand in terms of the square of the value u, and you get this interesting equation. 1/24 h bar over kT squared. Difference in atomic masses divided by the product of masses times the force constant for the motion of this atom I in the molecule. All right, now let's consider this reaction hx and dy. So we just have to take the difference in this partition function, this ratio and this ratio, the two chemical species. Now you see the mass factor is the same, irrespective of the chemical species. This is the same. So the isotope fractionation has a mass factor, which depends on the isotopes you're talking about, times the difference in the force constant of a hydrogen or deuterium atom in the molecule HX and in the molecule HY. And this goes as 1 over T squared. And this is a first term in a series. And so at high temperatures, you get a 1 over T squared law. And at a low temperature, you get a 1 over T law. The next thing you see in this equation, that the isotope effect decreases with the square of the atomic weight of the element. It depends on only the mass difference of the isotopes and not the molecular weight, not the weight of any other atoms in the molecule. And it depends only on the difference in the force acting on the atom which undergoes isotopic substitution. So the entire beauty and utility of the isotope effect depends on the fact that it pinpoints the change in the force specifically of the atom for which there is isotopic substitution. So you can go around in a molecule and make isotopic substitution in every position, and I'll show that later, and you can map out what is happening in a chemical reaction, how the forces change. All right. Now, that looks all very well and good. Now, in 1943, Maria Mayer and I calculated that we might be able to separate isotopes by chemical means and get a separation factor about 1.001, and that would make it competitive with other methods. So after the war, Glenn Cluett and his group at Oak Ridge started such experiments, and they found a separation factor of 1.0013 for the exchange of uranyl ion and the reduced plus form of uranium. Now, the interesting thing that they found was the heavy isotope, U-238, concentrated in the plus 4 uranium state. And according to the Bigeleisen Mayer equation, the heavy isotope concentrates in the chemical species with the strongest bonding. So from that, you would say that the bonding of uranium hydrated in solution plus 4 uranium is stronger than the chemical bonding in the uranyl ion. So people then said we don't really know about salvation in species like that, and that remained an enigma for many years. Now, in 1989, by 1989, the Japanese had worked hard on this process discovered by Cluett, and they actually had already built a pilot plant to separate uranium isotopes by chemical means. And one of the collaborators, Professor Fuji, along with the people at a Psy Chemical Company, measured the separation factor for a number of isotopes relative to U-238. So for U-238, there's no separation factor U-238 against it. U-236, U-234. They form a good straight line, just depending on the mass difference. But you see, 235 is significantly above the line. And later, Fuji published more experiments, and he did experiments with U-233 and U-232. And here's our U-235 friend. Here's U-233. Here's U-232 on the line. So, we've got a new problem. This isotope effect does not go linear with the mass. Now, Fuji's original explanation was that this was due to the nuclear spin. Well, I thought about this, and I made a back-of-the-envelope calculation. I came to the conclusion that that was, couldn't be true. And subsequently, I got spectroscopic information from my friend Clyde Hutchison about the nuclear spin splitting in uranium for U-235, and I calculated how it was much too small effect. And then it came to me that, oh yes, in the heavy elements, you have large shifts in the atomic energy levels due to differences in nuclear size and nuclear shape. That's known as the nuclear field shift. And if you have two isotopes of the same element, and this is a light isotope, this is a heavy element isotope, they have different nuclear radii. And if you have an atom with an appreciable electron density in the nucleus, the light isotope binds the electrons more than the heavy isotope. And so then you'll have an energy difference in the chemical reaction. And that's going to change things. So, here's an example of the kind of isotope shifts that are known from atomic spectrum. You see here's mercury, even isotopes, evenly spaced. Here are the odd isotopes displaced to lower atomic number. Here's uranium, known, samarium, lead, and so on. Well, so when I started to work on this, there have been spectroscopic measurements on uranium vapor, and I was able to develop the theory and see how this would affect the exchange reaction between U4 and U6. And so there's this standard vibrational problem that I spoke about earlier, which is linear in the mass. And now there's this problem in addition to the field shift. And from the field shift, you find that the heavy isotope concentrates in the chemical species with the smallest number of s electrons in the bonding orbit. Well, there you have the clue. The uranyl ion has 6 s electrons in the bonding orbital, and the +4 uranium has at most 2. So the U-238 concentrates in the U4 species, and that's one qualitative thing. And then I was able to calculate out this effect, and here we are. Here's the results of that. I did this from experimental data on this ratio. That's taken unity, and these are the experimental values for the other isotopes. And here, the values I calculated at this temperature, just using this theory, and the known spectroscopic shifts in the atomic spectrum, and you say you can't ask for anything better. So the thing I say now about this is if I had thought about this in 1943, and then it would have been impossible to calculate this, I would have told Yuri's assistant that this is an impossible problem and you can't do anything about it. So all my work on isotope chemistry would never have started. I would never have gotten into the field. So fortunately, not only did I overlook this, Maria Mayer overlooked it, Yuri overlooked it, Teller overlooked it, you name it. At any rate, we have that problem now. What I'd like to do now is talk to you briefly about application to chemical kinetics. And this is a problem that I worked on myself, not with Maria Mayer, but it used the methods that Maria Mayer and I developed for equilibrium systems. And some of the kinds of problems that you can address by isotope studies in chemical kinetics is you can, because isotopes can tell you about potential energy sources. Well, first I want to, pardon me, let me show you a slide. We have the next slide, I think that may be the last slide. Oh, let's do it. Let's go skip that. Pardon me, I put this in backwards. Let's skip that. Very good, thank you. In chemical kinetics now, you start with a reactant, you have a transition state, you have a product, there are 0-point energy levels and other levels in the ground state. And apart from the reaction coordinate, the other coordinates have vibrational energy. There's a zero energy level difference between the isotopes. And if we just consider the activation energy for a light isotope compared to heavy isotope, you see there's a difference in activation energy. And if this is the relative spacing of levels, the light isotope reacts faster than the heavy isotope if you just consider the 0-point energy effect. But in chemical kinetics, you have to also consider higher levels here. You also have to consider the fact that for reaction to go, you have to go across the barrier. And so you have to add a term for crossing the barrier. So when I got started on this problem in 1948, I said, well, this part of the problem, I know all about that. That's simple. In principle, I just applied the Bigeleisen Mayer equations now to the equilibrium between the F and transitions. And if I now add a crossing of the barrier, I now have the final answer. And I looked up and saw what people had done in the past, and there were these papers by Eugene Wigner, by Henry Iron, and they had done things by the Uri Greif method, and things were hopelessly complicated. And I showed that you could go through all of these, apply the relations about classical quantum mechanics and come down to my formulation. All right, that'll be all for that stuff. So, what can you do with isotopes? Well, one is you can, if you know the properties of the reactants, and you do some experiments, you can, in simple cases, map out the potential energy surface of the transition state. And we did this for the first time at Brookhaven using this reaction. One doesn't do this anymore now because you can calculate out potential energy surfaces by quantum mechanics and high-speed electronic computers, and you can do molecular beam scattering and so forth. And so this is of historical interest. Now, the more interesting thing is study reaction as a mechanism. And is an old transparency. So I'll show you some results on some of the classic studies on electrophilic, aromatic substitution, concerted versus sequential reactions, and then about some work done in the last couple of years in the application of kinetic isotope effects. Let's go to the electrophilic aromatic substitution. That was first studied by Lars Melander, Swede, then at the Nobel Institute. And he studied the tritium isotope effect in the nitration of benzene. And the mechanism for that reaction had been postulated independently by Ingold and Frank Westheimer. There is a pre-equilibrium in which the electrophile, that's nitronium ion in that case, adds the aromatic ring. And then there's a proton extraction by the base to get the product. And using a steady state approximation, you have the observed rate constant is this rate, the forward rate, divided by the ratio of return of this to decomposition. Now, when return is fast compared to this, then the rate constant observed measures this, and then you should only observe a small secondary isotope effect, and that's what Melander observed. So that showed that in this nitration reaction, the rate determining step is the rate constant is simply K. Now in some beautiful experiments in the 50s using deuterium, Zollinger, then at SIBA, and then at ETH, found reactions in which K minus 1 was large compared to K2B, and this ratio large compared to 1. So the observed rate constant is K1 over K minus 1 times K2. So now the isotope effect is primarily dependent on the proton extraction, and that is a bond breaking reaction, and that then should show a large isotope, and that's what he observed, an isotope effect of a factor of 6, and that proved that mechanism. Well, another interesting study was by Stanley Seltzer, Brookhaven, who examined the possibility of studying concerted versus two-step reactions. And he did secondary deuterium isotope effects and nitrogen isotope effects, and this decomposition. And reaction showed this is the slow step, and this is the fast step. Now the question Dr. Seltzer raised is, do you break these two bonds in a concerted fraction, or do you break one and then the other? Now, he compared the case where you have the substitution on both of these carbon atoms was compared to one. You see, that's essentially twice the effect here. So that shows that these two break at the same time. Then he put deuterium here and none here, got practically no effect, and that showed that this bond breaks first, and then this one breaks. So you have an example of concerted versus two-step reactions. An interesting application of this has been made recently in some collaborative work between Dan Singleton and Out. And they studied the Diels-Alder reaction between isoprene and maleic anhydride. And the pink circles are all experimental values, the ones that have numbers. And the blue ones are ones calculated by quantum chemistry and the theory of the kinetic isotope effect. And he measured the kinetic isotope effect both for deuterium and carbon-13 at various places in the molecule and compared them with calculations. And these numbers here are the statistical significance of these calculations. Now that's a beautiful example of what you can do there. Examining position by position, small isotope effect, and a complicated reaction by comparing theory and experiment. Now, another interesting case that they've gone into has been this question of the hydration of an olefin catalyzed by osmium tetroxide. And there has been a controversy between Sharpless and E.J. Corey. And Sharpless said this was a 2+2 reaction, and Corey said this was a 3+2 cycle addition. So Sharpless, in a very objective way, got together with Houck and Singleton, and they measured kinetic isotope effects. And they calculated it for the 3+2 and the 2+2 reaction. And here's the experiment. So don't need to look very far. Here's the experiment. Here's the 3+2. And so that showed conclusively that the Corey mechanism is correct. That shows you what the power is of the kinetic isotope effect. And combined with theory and studying the mechanism of a chemical reaction. Now, to give credit, all of these theoretical calculations depend on the computer programs by my colleague and friend Max Wolfsberg, who makes these programs available freely to anyone who wants to use them. Now, this slide says you can use isotope chemistry for anthropology. Well, how do you do that? And why would you be interested in it? Well, this is Lexington, Kentucky, and there are people around here that are interested in horses. Well, who am I to tell people about horses? I don't know much about horses. But anthropologists want to know what people ate in the past. And the reason they want to know that is that tells them something about societies and what culture was like. And you can find out about that by doing isotope chemistry. Near in 1939 found out that in light elements, isotope abundance in nature is not constant, and it depends on chemical species. So people working with Professor Robert know about that. They found out a case of sulfur. But here's a case of sulfur studied by Thode in around 1950. And here's sulfur ratio and sulfate going all the way down to sulfides. And the heavy isotope, sulfur 34, concentrates the chemical species with the strongest bonding. Just as I said earlier, you can calculate that out. So isotope chemistry in nature depends on chemistry, and so you can learn something about chemistry of natural materials by measuring isotope ratios. Now, what did ancient peoples and animals eat? All plant and animal food, as far as the carbon is concerned, is derived from CO2 by photosynthesis. We're going to define the quantity del, which these isotope anthropologists use, which is the carbon-13 to carbon-12 ratio. And that's 1,000 times the difference in this ratio in an unknown sample minus that in the standard, divided by that in the standard. Now, there are two photosynthetic cycles. There's the C3 Calvin cycle, which have plants, leafy, woody, and other soft plants, in cool growing and aquatic grasses, wheat, beans. And they have del values which range from minus 36 to minus 22. So this is 3%, is 2%. It's a small effect, but I can tell you right now that people can measure del. 1 del is a 10th of a percent. They can measure that to 1/10 of that, or 100th of a percent, on a routine basis, every day in the week. Very sensitive. Now there's also the C4 cycle, which are tropical and temperate grasses, and they have del values of So you can see right away that you could tell whether somebody is eating C3 or C4 foods or some combination. Provide the record is kept. Now, one of the great people in this work is Sam Epstein from Caltech. And he is his student, Mike De Niro, through a bunch of different kind of animals in the laboratory, small animals, starting from shrimp, nematodes, flies, moths, snails, grasshoppers, and even a mouse. And they fed them different kinds of food, starting from C3 foods, C4 foods to C3 foods. And this is the Del value of the material they fed them. And after they grew these animals a while, they sacrificed them and measured the Del values of the animal body. And you see there's a one-on-one correlation between what the animal ate and what his carbon content of his body is. So if you measure this, you know this. Well, earlier this year, I read a report from some anthropologists who measured some Del values for carbon-13 from horses that lived 5 million years ago in the Blue Valley of Florida. They looked at the skeletons, and up until their work, anthropologists would look at the teeth, see the size of the teeth, and how many scratches there were. If there were a lot of micro scratches, that meant that they ate grasses. Otherwise, which then would be C4 photosynthesis. If there weren't any, not many, then they were ate woody and leafy plants. Now, the ones that ate grasses are naturally called grazers, and the one that ate plants, of course, you eat that when there's no grass around, right? And they're called browsers. So this is sort of a classification of the horses that they studied based on examining teeth. There was this group here they called grazers, which are then C4 plants, and these are browsers, C3. So they measured isotope ratios of these teeth on a number of different kinds of horses. These were very small horses in other states. They only weighed from 50 to 250 kilograms. Not very good for the Kentucky Derby. But anyway, all these horses on the basis of tooth examination have been considered grazers. And by examining the microscratches and C13, they came to the conclusion that only this species was a pure grazer. These were C3 and C4 combination, grazer and browser. And these ones were browsers. And I'll now show you the actual detailed isotopic analysis. Here you see the browsers, and you see they concentrate. The larger del values. And here are the grazers, and they concentrate the lower del values, that C4 diet. And of course, you have ones that are eating mixed diets. So, you see, even determining what horses go, you can do something with isotope chemistry. Well, I'm getting sort of out of wind. I've tried your patience long enough, so I'll stop here and just summarize here what I said. Grazers, grazer browsers. And actually there have been studies about what ancient peoples ate and so on, but I won't come into that now. And this is only a short overview of what we can do now in isotope chemistry. I thank you.
I think, considering the time, if any of us have any questions, we can come up and ask Dr. Bigeleisen ourselves. So let's just thank him again for his time.
Thank you.